Hello and welcome to a new video on cryptography for everybody. In a previous video, we created an AES cipher that used only classical ciphers as its building blocks. And this was just a fun idea to create such a cipher. At that time I thought, why couldn't we replace every modern component in the AES by, as I said, a classical cipher? So I did this and I created a video about that. And I also published an article on my blog. So if you're interested in reading this article, I will also link it below this video. And I got a comment below this article asking for, you could say, the opposite idea. Not taking a modern cipher and replace all of its components by classical ciphers, but take a classical cipher, for instance a Rotor cipher machine, like the Enigma, and bring it to the modern world, meaning, for instance, create rotors having more than the 26 contacts, so being able to encrypt more symbols than the 26 Latin letters. Yeah, and I did this. I created different Enigma machines, of course virtual Enigma machines using C#, and these machines are different. They have more pin contacts at each rotor, and they are able to encrypt more than the usual 26 letters. And in this video, we will first discuss how the Enigma machine can be formalized, and then how I extended the idea of the Enigma machine into the modern world. I structured this video into 6 different parts. In the first part, we will have a small motivation. Then we will discuss the so-called Enigma Equations, and these are the way to formalize the Enigma and to create equations for this. Then we will have a look at the first new Enigma I created, the so-called Morse Enigma. Then we will have a look at the Enigma 64. And finally we will have a look at the ASCII Enigma, which is able to encrypt arbitrary ASCII symbols. And finally, of course, I will show the source code, walk through it and discuss it. The Enigma machine was already broken in its time of usage by the Allies. And to break the Enigma machine, so-called Turing bombs were used to perform known plaintext attacks using so-called crypts, which are known parts of plaintext. You can see such a Turing bomb here, which is shown in Bletchley Park, where they use these Turing bombs to actually break the Enigma machine. And on this channel we had already 3 videos on the Enigma machine. The first video was about the functionality, the second video was about the cryptanalysis, and then the third video was about new attacks that we implemented in Cryptool 2. Today we can attack the Enigma machine in a ciphertext only scenario also using modern techniques like hill climbing and simulated annealing. And the cryptanalysis video and the new attacks video also show these kind of attacks that are implemented in Cryptool 2. Now let's motivate the new Enigmas. As I said, a classical Enigma used rotors, and each of these rotors has 26 pins. And the idea was, and the question is, how secure would an Enigma be if it uses today, or used in its time, more than 26 pins that are actual letters then, or replace or define the letter replacements per rotor. And as I also already said, I designed 3 different hypothetical Enigma machines having rotors with many more of these pins. Let's first have a look at the Enigma equations and how we can formalize the Enigma. And the Enigma machine can be formalized easily. First, we need some definitions. For letters, I use numbers instead of letters. So the 0 is the A, the 1 is a B, a 2 is a C, and so on and so forth. And the last letter in the Latin alphabet, the 25, is the Z. And when we use more than the standard 26-letter Latin alphabet, we just keep on counting the letters or the numbers of the letters in our alphabet. Our plaintext letter is defined as P, and our ciphertext letter is defined as C. And then we need the length of an array. An array is a data structure it's just a list of, for instance, integers, and we define the length of an array as a function called len, and then as a parameter it gets the array. For instance, an array x length is defined as len of x. Then we have a look at the rotor equation. First of all, a rotor R is defined as an integer array. For example, this here, we have at the first position 16, then 3, 25, 1, 9, and so on, and the fourth, and then 8. All our alphabet letters or digits or integers are in this rotor array. And of course, they are shuffled because we want our rotor to shuffle our letters, also to encrypt our letters. And then a rotor, of course, in the Enigma machine has a rotation, and the rotation is defined as R. And of course, a rotor's rotation is between 0, so it's non-rotated, and the length of the rotor minus 1. And then the rotor equation is defined as the ciphertext letter equals, and then we have a lookup in our rotor array at the position of the plaintext. Remember, p is also an integer number, plus the rotation number modulo the len of our rotor array. This gives us a value from that array. Remember, these are also numbers or integers. Then we subtract from this number here again the rotation and compute the modulo again of the length of the rotor. This is the rotor equation. I think it's quite short and quite easy. And you will see, or you see here, that the modulo is used that we do not go out of our array. So when we go out of our array on the right side, the modulo takes care that we come back from the left side. And when we go out by subtraction on the left side of the array, due to the modulo, we come back on the right side into our array. So we will have never here a problem with the lookup in the array because of the modulus. And this takes care that we go from the left or right side again into the array. Remember, it's like with the real rotor that goes around. When you go around, then you start again at the beginning. And then, of course, we do not only need a rotor, we also need inverse rotors because, and that we will see later, the current goes forward through the rotors and then backwards. And the inverse rotor R to the power of minus 1 is the inverse rotor function of R. Meaning, when we encrypt with a rotor, for instance, the number 4, and we get a 16 with a specific rotation, then when we use the inverse rotor and we put in the 16, we get back the 4, and so on and so forth. For each rotor, we have an inverse rotor. Then for the Enigma machine, we need the plugboard. And the plugboard px is a self-inverse function that exchanges a given letter x by another letter. For instance, that means if any letter A is replaced by B, since this is a self-inverse function, then the letter B is also replaced by A by this function. And this is the plugboard of the Enigma. And with the Enigma machine, this was done with cables and plugs that you put in the plugboard. If you're interested in how the Enigma machine works in detail, I suggest that you have a look at my Enigma introduction video. And finally, we need a so-called reflector. So the current goes into the Enigma machine, and of course it has to come back out of the machine so that a bulb flashes when we press a key on the Enigma. And for that it comes back, we need a reflector. And a reflector is basically also a rotor, but it is also self-inverse. So like a plugboard, if A goes into that reflector and B comes out, also when we put B into the reflector, A has to come out. And of course the reflector has to be defined for all of the letters. The plugboard has not to be defined for all of the letters. Of course it has to be defined, but imagine you only plug in one plug into the plugboard, you exchange A by B and B by A, then all the other letters like C, D and so on, when you put these into the plugboard, they just return. So if you put a C into the plugboard, you get C, a D, you get D and so on. But with the reflector, every letter has to be replaced by another letter and vice versa. Now that we know the building blocks of the Enigma machine, we can have a look at the complete Enigma machine. And I made a drawing of the machine that you can see here. So at first we have our plaintext ladder here and a ciphertext ladder that comes out of the machine. We put the plaintext ladder into the plug board and it gets maybe replaced, maybe not. Then we go through the first rotor where it gets replaced, through the second rotor and through the third rotor. Keep in mind that this machine is a 3-rotor machine. The Enigma machine was also built using 4 rotors, and with my code I show you later, you can even build Enigma machines with hundreds of rotors if you like. Then, when it comes out of the rotor 3, it gets into the reflector and is sent back through the rotors. So it goes through the rotor R3, but in that case it has to be the inverse rotor here. And here's the same, inverse rotor R2, inverse rotor R1, and then the plug board. Of course, electromechanically, these were all the same rotors. But when you program this and use these as functions, you have to program these as rotors and inverse rotor functions. And here we have the final Enigma equation. Our ciphertext letter C is, and then we have this really big expression here. But as you can see, I colored these that you see where these functions come from. And you have to go from the most inner function to the outer function. First, our letter goes through the plug board, then rotor 1, rotor 2, rotor 3. Then it goes through the reflector, and I just see here's a small error. It's not the inverse reflector. It could be the inverse reflector because the reflector is self-inverse. That means that RF equals to RF to the power of -1. But we could just remove the -1 here. Then it goes through the inverse reflector 3, the inverse reflector 2, the inverse reflector 1, and then again through the plug board. And this is the Enigma equation. And clearly, each of these rotors has a current rotation value. And when a rotor rotates, it has notches to also rotate the next rotors. So if we would only use this here, then we would have a static Enigma. It would be just a simple monoalphabetic substitution, because every time you would send in a plaintext letter, then you would get out the same ciphertext letter. To get a real Enigma, we have to rotate these rotors. And remember, we defined our rotor as having rotations. And each rotor has notches. And these notches take care that when a rotor rotates in a specific position, for instance, the rotor 1 here rotates, and then when it rotated a specific amount of time and it hit a notch position, then it rotates the next rotor, and if this rotor hits a notch, it rotates the third rotor. And the third rotor also has notches, but of course the reflector does not move, so the notches are here not important. And with the notches, we discuss that later in the code section of the video. And some of the experts that watch this video and who are experts on or of the Enigma machine will now say, but you omitted the so-called rings of the rotors. Yes, I made my life a little easier by removing the rings, because the rings are cryptographically irrelevant. That's why we don't have these in this video and also not in my implementation in C# later on. Now let's have a look at the first Enigma machine or virtual Enigma machine that I implemented. And that machine I called the Morse Enigma. Why did I call this the Morse Enigma? First, I wanted to design an Enigma machine which ciphertext still can be sent using Morse code. Remember, the Enigma machine was used to encrypt letters during wartime, and then the ciphertexts were sent using Morse code. And I thought, would it be possible to create such a machine that also can be used to create texts that can be sent via Morse code? And that's why I defined the Enigma alphabet like this. We have all the uppercase letters here from A to Z. Then we have the digits from 0 to 9. And we have 4 special characters that can be used to lay out our text, like a full stop, a comma, exclamation mark, and so on. And here are the basic ideas of this machine. First of all, I think that this machine could have been built in its original time. The machine would have removed the problem of needing to write 1, 2, 3 in the plaintexts. So when they wanted to send numbers, it was very tedious because they had to write out the numbers, because with original Enigma machines you didn't have digits. With my machine here, this would solve this problem. Then plaintext could have been formatted using dot and comma instead of using X, what they did in the time. And then ciphertext could have still be sent using Morse code, I already said that, because all symbols that I have chosen here are available in the Morse code. And probably the machine would be harder to cryptanalyze since it has 38 instead of 26 letters per rotor, rendering the key space much bigger than the original key space of the Enigma machines in that time. Let's have a look at the next Enigma machine. And as I said, we will also have a look at all of these machines in the source code. So the second machine I wanted to design was a machine which ciphertext still can be sent as text today. And that means that the symbols of the machine are printable symbols. And so I defined the Enigma 64th alphabet as the Latin uppercase alphabet, then the lowercase alphabet, also the digits, and I added 2 special characters, the point and the comma. And then we have 64 different symbols. I could have used also 2 different special characters, and then I would have base 64 encoding. But I have chosen the full stop and the comma because I wanted to be able to lay out or to write better plain texts. And the basic ideas of this machine is that the machine has 64 different printable characters. The plain text could be formatted using dot and comma instead of X also. And the ciphertext can still be sent as text since all symbols are printable symbols. And probably the machine would be even harder to cryptanalyze even today since it has 64 instead of 26 letters per rotor, even increasing the key space of the Enigma machine. And then we have the ultimate modern Enigma machine, which I call the ASCII Enigma. And the ASCII code you can see here. That was the third idea. I wanted to design an Enigma which works on the complete ASCII encoding. And the ASCII Enigma's alphabet is therefore 8-bit symbols that are 256 symbols from 0 to 255. And this here is the ASCII code. I copied this from the Wikipedia. Here you have all the possible symbols that can be encrypted. So you could use this machine really to encrypt binary data. And the basic ideas were the machine uses the complete ASCII encoding, as I said, a binary Enigma. Then the ciphertext cannot be sent directly as text, that's a problem, due to non-printable ASCII symbols. And that's why the ciphertext needed to be converted to base 64, for instance, to be sent as text, or saved into a binary file before sending. And probably this machine would be very, very hard to cryptanalyze since it has 256 instead of only 26 letters per rotor. This is the so-called ASCII Enigma. Now that we have seen all my Enigma implementations or the ideas for the implementations, we will have a look at the implementation later, and we know how the Enigma equations work, let's have a look at the C# implementations of the different Enigmas I built and play a little with the code. And if you're interested to get your hands on these implementations, of course, I uploaded the source code to GitHub. You can find the source code here with this address, with this URL, but I will also put the link below this video. So let's have a look at the Enigma implementations. I'm here now on the desktop of my recording PC, and I want to show you the C# implementation, but before we can do so, I first need to delete this file here, and then we can check out or clone the repository by using git clone here. I use Rotors git, and I already have, don't ask me again, or remind me later, I have installed this Rotors git, and I have the URL here of the ASCII Enigma, so let's clone it. Then we have a C# Visual Studio project here. You can just start the ASCII Enigma SLN file and it should open your Visual Studio. I'm here now in Visual Studio. I opened the ASCII Enigma solution, the project here, and we have different files here, and we will go one by one through these files and see how this works. And the most important file probably for the definition of the enigmas is the so-called constants file. Because in the constants file, you can see different constants, and I have, for instance, here all the alphabets. I have the alphabet 26, which is the 26 letter Latin alphabet. Then I have the alphabet M for the Morse Enigma, and I have the alphabet 64 for the Enigma with the 64 pin rotors. And finally, it's a little different here with the alphabet for the ASCII, because you cannot put all the ASCII symbols since there are some non-printable characters in this alphabet, and that's why we created an integer array, and it goes from 0 to 255. Then we have different static classes that are only classes with definitions of the Enigma. For fun, I put the original Enigma M1 or the original Enigma 1 here into this project also. So you have the original rotors of the original Enigma 1. You have here the notch definitions. That's also interesting. These are the numbers of the rotation. So the rotation numbers when a rotor rotates the next rotor in the rotor block. And then you have here different reflectors. These are U, K, and W. This means in German Umkehrwalze. This is just reflector. We have reflector A, B, and C. Then we have the Morse Enigma. And here you start to see different rotor definitions, because in this rotor definitions we also have the digits and the special characters. And I decided for all of my rotors of all my new Enigma machines that they need a minimum of 2 positions where they rotate the next rotors. These are the notches for these rotors. And then of course we have a reflector, which is just an inverse alphabet, putting each letter to its inverse letter and itself inverse. So that's why I just put the reversed alphabet into this reflector. Then we have the Enigma 64, and you see the rotor definitions start to get very huge, very big. And we also have different notches, and here we have the reflector, again, the reversed alphabet. And finally, we have the ASCII Enigma, and with the ASCII Enigma, due to the non-printable characters, it's a little different. We only have integer arrays here, and we have all the mappings here with numbers, and you can see that this is really huge. We have 256 numbers in each of these definitions, and also due to the huge size of the rotors, we have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7 notches in these machines here. So at seven positions, this machine will, or these rotors will rotate the next rotors. Now let's have a look at first at the program itself. And in the program we have what I call test methods. These are not actual C# tests. These are just methods that I implemented that will print out the test cases or the tests that I perform with these machines. And for fun, let's just start it, that we can see what happened. So it first gets compiled, and here we have the output. And of course, so we have the Enigma 1 here. Hello world, this is a test text that gets encrypted and then decrypted. And to be sure that the implementation is correct, I used Cryptool 2 to verify my implementation. Then I have a test for the Enigma, the Morse Enigma here. And you can see here, you can put comma into your text. This gets encrypted then, and it also gets successfully decrypted. Then we have the same test here for the Enigma 64, where you can see also that the encryption uses a complete alphabet, and we can decrypt this successfully. And finally, we have a test of the ASCII Enigma. And since these here are, or this output can also contain non-printable characters, instead of printing it to the screen, I print out the integer values of all of the letters here. And then the decryption, of course, since I put text data into the ASCII Enigma, we get out text data. But you could use the ASCII Enigma also to encrypt arbitrary files. Now let's have a look at the implementation a little closer. And as I said, we have these test methods here, 1, 2, 3, and 4. And we have test Enigma 1, Morse Enigma, Enigma 64, ASCII Enigma. Let's have a look at the Enigma 1. So you first have to define your key. The key is the starting position of the rotor. So I have a 3-rotor Enigma here. The Enigma 1 is a 3-rotor Enigma. And as start key, I have chosen A, B, and C. So A is 0, B is 1, C is 2. I also have convenient methods where you can put in strings that are then converted to these numbers. But in this case, I used the strings. Then also part of the key is the definition which plugs are plugged into the plug board. I wanted to plug A with B, so I have 0, 1 as a plug. C with D, so I have 2 and 3. And E and F, which is 4 and 5. These are the plugs. Then we have to create the rotors for our machine. And we have to create a new rotor. And the rotor uses the Enigma 1 rotor 1, of course. And this method here, map text into number space, just takes the text representation of the rotor and the alphabet 26 and creates integer arrays. As I said, the implementation internally works on integer arrays. Then, of course, the rotor definition needs, or the creation of the rotor needs the notches. So I have rotor 1 notches. And the 0 here is just the start rotation. Since I later put in the key, I put the start rotation of the rotors all to A. And then we need a reflector. And the reflector I've chosen is the reflector A, Umkehrwalze A. And a reflector in our code is also the same as a usual rotor, it's just a rotor. It has no notches, so I put null into it. It doesn't rotate also. And it can have a start position, so you can actually rotate the reflector in the machine, but of course it's set to 0. And then we create a new rotor machine object, which gets the rotors here as an array, a list of rotors you can say, a reflector, a plug board with the definition of our plugs here, and finally it needs the alphabet the Enigma machine operates on. In our case here with the Enigma 1, it's a 26-letter alphabet. And then also in the constructor here as a parameter we define the key here that we give. And then it's just encryption and decryption. We have our test text here. It gets printed out to the console. We convert our text using the alphabet 26 to a plain text array. It's an integer array. As I said, everything integer arrays. Then the ciphertext is produced by calling a method on the Enigma 1. It's called crypttext. You know, encryption and decryption with the Enigma machine is the same method. It's a self-inverse machine. And I put in the plain text. Then I write to the console the ciphertext that I got, but of course I have to map it back into text space using the alphabet 26. Then I reset the machine by setting the key to the original key. And then I decrypt my ciphertext again using the Enigma 1 with crypttext. And finally, I print out the decrypted text and I use, of course, again here the map numbers into text space method to map from integer arrays to string using the 26-letter alphabet. And this is the same with all the Enigma machines. The Morse Enigma then has a bigger key since I used 4 rotors for the Morse Enigma machine. I have here rotor A, B, C, and D of the Enigma Morse. I create again the Enigma machine and I do the same. I encrypt it here, convert between string and integer array and vice versa. Then I decrypt here, and finally I write the decrypted ciphertext or the plain text again to the console. This is the Morse Enigma. Then we have the same again with the Enigma 64, also 4 rotors. Keep in mind each of these Enigma machines has its own reflector, and it works the same, encryption, decryption. And finally the ASCII Enigma is a 3-rotor machine in this case again, with rotor A, B, and C of the ASCII Enigma and a plug board. I think with these machines I didn't use a plug board. Yeah, that's right. So this is I have here an empty plug board for the ASCII Enigma. And then I have hello world. This is the test text again that gets encrypted by the ASCII Enigma machine and decrypted by the ASCII Enigma machine. And in every of these methods here, you have the tests that should come out with the settings that I created here. If you want to add a new rotor, for instance, to your machine, you could just copy one of the rotors here. Name this, for instance, rotor X. And then we have the ASCII rotor. And we have rotor... Oh, we have a rotor D. We can use this as a fourth, rotor D. Then, of course, you need rotor D notches here. And the funny thing is that you could also define a rotor 4 with rotor D alphabet, but you could use the notches from the other rotors. In fact, that means you can create many more rotors. By the way, if you want to create a rotor by your own, there's also a help method in these other classes to create random arrays based on alphabets. And then it's just a matter of adding a new entry into our key, since we have a fourth rotor. So this is one, this is B, C, D, E here as a start key. Then we have to provide the rotor also to our machine here. And now when we press, when we start this, we should get, yeah, you see here 166, 16, 20. We have now 43, 64, 243. This is a different ciphertext. That means that it used the fourth rotor. Now let's have a brief look, I think, at the rotor class. The rotor class is the heart of the Enigma, since the Enigma's heart are the rotors. And in the rotor class, you find our Enigma equation here. And that is here in the encrypt and decrypt methods. And of course, encrypt and decrypt. Yeah, okay. Why does a rotor have encrypt and decrypt? The rotor has encrypt and decrypt since it uses for the encrypt the actual rotor and for the decrypt the inverse rotor. And that's why it has encrypt and decrypt methods. And when you create a rotor, then you provide the rotor here, that is this integer array here. And the inverse rotor is also automatically generated by a helper function internally. So you don't have to provide the inverse rotor definition. This class takes care for that. You just give the usual rotor array, the rotor string, or in this case, the integer array, to the rotor when you create it, and then you automatically get the inverse rotor. And then we have rotation that we can set of this rotor. And we have a step method, and this step method just puts or adds 1 to the rotation, and it takes care that you don't run out of the rotor using a mod function, and it uses mod the rotor length here. And then we have this helper function also, is it at a notch position, and this is later used by the rotor machine class. Let's have a look at the plugboard. The plugboard is a really simple class. You just get you just put plugs into that class in the constructor, and it creates the plug mappings for you. And we have two constructors here. One, you can provide a string for the alphabet, and one, the integer array. And then the decryption is just a lookup in our plugs array to get the letter out of the plugs. Then we have the rotor machine class. The rotor machine class just has a plugboard, an array of rotors, and of course a single reflector. So all of our rotor machines are in principle Enigma machines. But as I said, you can provide as many rotors as you want. You could even create an Enigma machine with only one rotor, or you could create an Enigma machine having 1000 rotors. And when we crypt here, we have a crypt text method that encrypts and decrypts a complete text. It goes through the complete text and always calls the crypt letter method. And the crypt letter method is a method that first steps all of our rotors. So it goes through the rotor array, steps always the first rotor, and looks if the next rotor needs to step, looks if the next rotor needs to step, and so on. So it takes care of the stepping. Then we have the encryption and decryption. First we go through the plugboard, then we go through all of the rotors, then we go back, because we go through the reflector, backwards through the rotors. That's why we need a decrypt method at each rotor, and finally we go again through the plug board, and then we return the ladder. This is a complete implementation of Enigma machines with arbitrary numbers of rotors. And the last thing I can show you is the util class, but I will just tell you here we have many helpful methods like the mathematical modulo method, because C# does not implement it in the mathematical way because it has negative numbers with the modulo operator, so you have to define or redefine the modulo operator for yourself. Then I have many help functions, for instance, map numbers into text space that maps a given number array back to a string, or map text into number space, and so on. So these are a lot of helpful methods, and I also extended, for instance, the integer array with index of that is needed. Here's a shuffle method I previously told you, where you can shuffle integer arrays and so on and so forth. Yeah, and you could now just go to the GitHub, clone the repository, and create your own rotor cipher machines if you want. You can also extend it with the rings. As I said, the rings are cryptographically have no impact on the strength of the Enigma machine, so that's why I omitted these. The rings would make the implementation more difficult, so as I said, I omitted these. Yeah, and this is everything I wanted to show you in this video. I hope you like it. If yes, please give a thumbs up. Also, if you did not yet subscribe to this channel, please do so. This really helps us to grow the channel and to make Crypto 2, what we use on this channel, quite often more popular. Also, press the bell to be notified when I upload new videos like this. Yeah, and as I said, thank you very much for watching, and see you in the next video.